listen-only mode.
Good afternoon, everyone, and welcome to today's webinar on Delta T management, presented by David Kandel. Be sure that you have turned up your speakers or dialed into the conference line in order to hear today's presentation. The conference line information can be found in the audio pod on your screen. Just as a friendly reminder, these webinars are recorded for future use. At the end of the presentation, we will have a question and answer session. Without further ado, I would like to introduce you to David Kandel.
Thanks, Lisa. Good morning or good afternoon to everybody. Thanks for joining us. This is, I guess, our second webinar in this series on the BELIMO energy valve. Today we're going to discuss the Delta T Manager and how managing Delta T as a strategy can help you conserve energy in your facilities. So we'll go ahead and get started here. As Lisa said, if there's questions, just sort of catalog them in your head or type them into the chat. I guess the chat opens up later, and then we can get those questions at the end. So let's get started. What is the BELIMO energy valve? If you're completely new to this product, the BELIMO energy valve is an electronically pressure-independent control valve, and it has an integrated BTU meter in it. And what this allows us to do, a handful of things. Obviously, with a BTU meter in place, we're able to measure energy and get a much more precise read on what's happening at whatever piece of equipment we put this valve on, so our air handlers or fan coils or heat exchangers or what have you. It also allows us to be pressure independent or temperature independent using either flow control or power control. We'll have a webinar later this year that delves more deeply into those two features. And then the third thing that we're really excited about with Energy Valve is Delta T management. And Delta T management essentially allows you to use less water to create the same amount of heating or cooling in your space by promoting a more efficient heat transfer process at your coil. And that is going to be the focus of today's discussion. If you joined us about a month ago when we introduced the Energy Valve, some of these slides will be similar, but I promise you that there's plenty of good stuff in here, so don't get frustrated if you feel like you saw some of this before. Let's start talking about low delta T and what it really means when we sense low delta T at the coil. If we have a low delta T at the coil, it's an indicator that we have an inefficient heat transfer process. And what that really means is we're using more water than we need to satisfy the BTU demand of the load. And so the other way to look at that is that we've increased our flow rate, but we haven't increased the amount of BTUs that are being exchanged into the space. And when we increase our flow, we obviously create a handful of issues in terms of energy. Most simply, we need to have more pump horsepower used. We need more flow. We're creating more pump heads, so we're taxing the pumps. But we're also going to get a reduction in the efficiency of the plant itself. And so there's a couple of places where we would be concerned about consuming additional energies. To understand exactly how this comes into play, let's take a look at the performance of a typical heat exchange coil. So we'll just call this an air handler coil. In this case, we're looking at a chilled water coil, but we would have a similar performance on a hot water coil as well. So what we're looking at here across the x-axis, we're increasing the flow through that coil. And then on the y-axis, we're increasing how much power, or B2H, is produced by that coil. And you could see a few things that are noteworthy about the performance of a coil. One is that at low flows, 5 to maybe 20 gallons a minute, this curve is quite steep in comparison to where it is later on in its flow. And what that is an indicator of is that heat is being transferred more efficiently. So small increases in flow create larger increases in the amount of heat that's exchanged. And if you think about how a coil is designed, or how it functions rather, this actually makes pretty good sense. A coil's a long piece of copper tube essentially, and we're going to take some really cold water in this case, as it's a chilled water coil, and if we put it through that coil really slowly, each molecule of water takes a long time to pass all the way through the coil and come out the other side. And so it has a substantially longer period of time in which it could exchange its heat. As we increase the volumetric flow rate, we also increase the linear velocity of the water, and that molecule of water now moves through the coil faster. So as we increase flow going left to right, we see that curve starts to flatten out because each molecule of water spends less and less time in the coil. Even though there's more molecules, obviously volumetrically we're increasing the number of molecules, but they're transferring heat less and less efficient as we increase the flow rate. This heat exchange process is governed by this formula, and most people in this industry are fairly comfortable or familiar with this formula, which is that the power output in BTUH is defined by 500 times the flow rate in GPM times the delta T in degrees Fahrenheit. So to really understand the exchange of BTUH to flow, we need to also examine how delta T plays into this. So we'll now plot delta T on this graph as well. So on the right side, we have increasing delta T readings in degrees Fahrenheit, and you can see that the delta T has sort of an opposite performance, but for the same reason as the coil. So remember, at low flows, our water was sitting for a long time in the coil and was transferring heat more efficiently, and therefore we have a higher delta T. As we push the water faster, we're going to be less efficient and have lower delta T. So what low delta T really means at a coil is that you didn't expend the energy in that water efficiently. So we spend a lot of money to make our water very cold. We put it through our coil, and maybe it's supposed to come out 12, 14, even 16 degrees warmer than we put it in, but it only comes out 8, 10, or 12 degrees warmer. Well, then we didn't use all of the energy that was available to us in that water, and so that's why we talk about inefficient heat transfer at the space. What's most interesting to look at is what would happen if we put even more water through this coil. What we're looking at right here is actually a fairly good heat exchange profile. But if we continue to flood more water into this coil, three things happen, and all of them are kind of bad for us. So let's go ahead and take a look at what happens. The first thing that happens, obviously, is that we're pumping more water. So we're going to increase our cost of pumping. The second thing that happens is that we continue to decrease our delta T performance, and the third thing that happens is that we stop producing additional BTUs in the space. So when we get to an area where we can produce the same amount of BTUs for varying volumes of water, we have an opportunity to use less water if we can control to specific parameters. And so that's why we're going to look specifically at delta T and try to make decisions about how we control water through that heat exchange device, because delta T is a fabulous indicator of the efficiency of the heat transfer. So if we go ahead and take a look at a point here, and that's right about, 58 gallons a minute or so, and then we extrapolate a line horizontally to all of the points in this point cloud that produce the same amount of BTUs as we did at, say, 58 gallons a minute, you can see that at some point during our heat exchange process, we did that amount of cooling at about 47, 48 gallons a minute, and sometimes we did it at as much as 65 gallons a minute. So we had this range between, say, 47 and 65 where we were able to produce the same amount of cooling in that space. And so the idea of delta T management is by examining delta T and forcing slower flows through there that we can utilize the lower end. Not that we'll always be able to use 47 gallons a minute, but more like we don't ever need to be at 65 gallons a minute. There's a misconception that this is a full load scenario and that there's no advantage to delta T limiting at partial loads, and that's just not true. So let's go take a look at a partial load point. Now, even on this particularly clean and concise data cloud of points, we can still draw a horizontal line across a pretty wide sweep of flow rates that produce the same amount of cooling in that space. And so even at lower loads, we can violate delta T and use less flow to create the cooling required even at lower loads. So this is a little hard to illustrate on this graph. What you're actually looking at on this graph is some data from a constant air volume coil on an air handler, and it's a very clean, well-knit data set. But if we take a look at something that's a little bit more typical and a little sloppy in terms of our heat exchange, like the one I've just popped up here on the screen, now we can go ahead and take a look at a partial load point and extrapolate a line horizontally, And now you'll see that even at this partial load, there's an enormous range of flows that were utilized. And we really want to be able to look at, I don't ever want to use anything off to the right there. And in this case, maybe we don't ever need to go past, we got 37, 38 gallons a minute to produce the load that's in place here. And so this is what we're talking about. It's not just a full flow, full load problem, because a lot of places don't run at high or load demands all the time, but you can still generate low delta T's even at partial load, especially in the shoulder seasons where our production of heating or well, really cooling, our production of cooling is much higher than the load demand in the space, and we wind up with low delta T's then. Can be really tricky to diagnose in a central plant type environment. Let's talk about what the potential impact of this energy savings would be if we could take a look at it both from the pumping perspective and the plant perspective. So let's start with the pump. And we'll take our clean looking curves and we're just going to pick 2 points on which we could control to relatively the same amount of cooling here. So point 1 on my graph uses about 55 gallons a minute, and it produces about 320 kilobTUs per hour. And so the second point on there, point 2, is closer to 65 gallons a minute, so about 10 GPM more. And we only produce about another 5,000 BTUH. So we're going to say that that 5,000 BTUH is somewhat negligible, but we'll take a look at how this breaks down statistically and what we spent to achieve this more heat exchange. So basically, percentage-wise, we gained less than 2% more BTU by spending 18% more GPM to get there, which begs the question, how many dollars does it cost to pump 18% more water? And in order to understand this, we're going to take a look at what's known as the pump affinity law. And the pump affinity law draws a relationship between the ratios of GPM, pump head, and pump horsepower, and scales them together. And basically, if you want to know what the increase in GPM versus the increase in pump horsepower is, you have to apply the ratio here, which includes a cube. And so 18% more water actually could wind up costing you in the neighborhood of 65% more pump horsepower or pumping dollars. And that's why we want to look at this. Small changes, because of that cubic exponential that's in there, small changes in the amount of flow that we're going to have percentage-wise can actually net us a fairly substantial amount of savings. So this would be the big way we could essentially start shifting our pumping costs lower. In this case, 2% more cooling or 1.5% more cooling is costing us 65% more dollars. If we had the ability or the knowledge to know that and make a decision about it, I don't think anybody would agree that that's a good investment. So if that's what's going on at the pump, what's going on at the plant? Well, let's talk about chillers first. Chillers are an interesting piece of equipment, and there's probably a ton of you on the call today that know a lot more about chillers than I do. But I think one of the things that we can say is that chiller plants are simply more efficient if they're operated at their design delta T than if they're not. And the reason I'm making such a generic and cryptic statement is that the impact of low delta T on a chiller is highly dependent on the chiller. So if you give me a 25-year-old screw chiller, I'm going to show you a huge energy penalty for operating it at a low delta T. If you show me a brand new high efficiency chiller that was purchased last week, I'm going to show you that it's much more versatile in terms of its efficiency operation with delta T. And so I don't want to really get into a deep discussion about that, except perhaps on a case-by-case basis. But again, it's going to work better if you give it what it's designed for than if you didn't. The other thing that's more tangible, though, is that if we have low delta T, which will cause these high flows, it can cause my chiller to stage improperly, and we should go ahead and take a look at that, because this would be a little bit more universal if you're running a plant that has multiple chillers. Let's just say, as an example, we have 2 chillers, and they're 500 tons apiece, so I have a 1,000-ton capability on my plant. And we'll say right now that we have a 500-ton load. And so we would have one chiller loaded at 100% to get this 500 tons. If we take a look at the GPMs, we see here on the left that GPM, this is just a reformulation of the 500 times GPM times delta T, except we've changed from BTUH to tons of cooling. We have GPM equaling tons times 24 divided by delta T in degrees Fahrenheit. If we go ahead and say that this is a 12-degree chiller and that it requires 12 degrees of delta T, if I'm at design, 500 tons of cooling nets 1,000 gallons a minute. What happens, though, if I have a low delta T? Let's say I go to 8 degrees of delta T. What does my flow look like? Well, because flow and delta T are inversely proportional when my load is fixed, or this big of a reduction in delta T causes a huge increase in GPM, and in this case, I now require 1,500 gallons a minute. And likely what has happened is that I have staged a second chiller because I need additional pumping capacity to get to 1,500 gallons a minute, even though I didn't need my second chiller to increase the load capacity of my plant. And so this is what we talk about when we say improper staging. Oftentimes you can wind up running extra equipment without your input, so to speak. It just sort of happens as a course of the way the pumping strategy is written. But the pumps run out of, are starving essentially, and so they request another pumping of another pump, even though the cooling requirement isn't there. Similarly, or not similarly, but if we're talking about heating, the biggest net benefit from a plant standpoint of delta T improvement would be on more advanced style condensing boilers. So condensing boiler works by preheating the return water by creating a condensing process of the flue gas over the relatively cool water that's returning from your coil. In a traditional boiler, we would just have the second stage fire heating area, and we would not preheat the water. So what the big function for condensing boilers needs to be is that that return water needs to be cool enough to create the condensation process in the first stage preheat. And so the lower the return water is, the higher the efficiency will be of your condensing boiler. And so this graph that we're putting up here, it's coming a little slowly, there it is, that we're going to put up is courtesy of ASHRAE, but each condensing boiler manufacturer is going to produce a similar type graph that shows the efficiency of your boiler based on your return, they call it inlet, but they mean inlet to the boiler. So for us, it's the return water temperature, and how as you get cooler and cooler, you get to the dew point inside of the condensing chamber, and then you can see there's a sharp increase in your condensing. So you can see on a graph like this, if they're condensing starting at 130 degree return water and we get down even just to 120 degrees, so 10 more degrees of delta T, we're taking efficiency from maybe 87 to 90 or 91%. So there's dollars to be had if we are getting better heat transfer at our coils. So in this case, we're pumping less and we're returning cooler water to our boiler, which helps the efficiency process. So how does the delta T manager work? The delta T manager inside the energy valve essentially monitors the temperature before and after the coil at all times. And as it does that, it's looking for a low limit threshold. So as you program the energy valve, you're going to say this is a 12 degree coil, or we know we can get enough heat transfer for what we need to do at 12 degrees F. And so we're going to set that within delta T manager. And so it will monitor and say, as long as we're above 12 degrees F of delta T, the valve can operate in response to the automation system. But if we violate that low limit threshold, in other words, if we get below 12 degrees of delta T, and it has to be significantly enough below that we're going to register. So if you go to 11.9, the energy valve's not going to do anything. But let's say in this case we get down to about 10.5 degrees of delta T. The energy valve with Delta T Manager engaged will suspend control of the automation system, and it will start to reduce its own flow until it has satisfied the 12 degrees of Delta T. And so in this case, we'll put a couple animations together here. I know this is a little slow for some of you, but let's say we have our overflows here, and then we're going to drive the flow lower. And as we do this, we raise the Delta T, and you can see at the top, we're trying to maintain the same amount of cooling into the space. So it is critical when you select, in this case, 12 degrees of Delta T, that you know or you're fairly confident that you can cool this space with this piece of equipment at 12 degrees of Delta T. So as an example, if I picked 16 degrees Delta T for this coil, I likely would be only able to produce about 75 or 80% of the capacity of this coil, which in some cases might be fine. Might be able to cool a space just fine with that. But in the case of this one, we were looking for the full capacity of that coil, and so 12 degrees F is what we're going to be able to do here. So this question comes up quite a bit, especially when I talk to contractors. Everybody gets a little fidgety when I say, hey, we're just going to ignore the control signal. So how can I let Delta T Manager limit the flow if it doesn't measure the discharge air temperature? What about the comfort of the space? And again, when we talked about the overflow, when we talked about generating low delta T, we said that that functionally caused 3 problems. One of them was we pumped too much water. The second one was that we had a low delta T problem. And the third one was that we produced no additional BTUs. So if we're able to just slice off the function, the portion of the curve where no more BTUs are produced, well, then we shouldn't have any adverse impact on room comfort. And again, you have to make an educated and smart decision about setting your delta T set point so that you won't run into this type of trouble. All right, so that's how it works functionally. The question is, does it really work? Can I save energy with this? So let's take a look at a few case studies that Belimo has put out. We have documentation available on energyvalve.com on all of the case studies we're going to present here today. But let's walk through them. The first one we're going to talk about is MIT University in Boston. So MIT University in Boston has a particularly difficult low delta T problem on their campus. And they engaged us with the energy valve to do a pilot project in one of their buildings, which was the Hayden Library. And the Hayden Library is about 150,000 square feet. It was built in the late 1940s, and we retrofitted 6 of the 7 air handlers that were in that space, which were getting an average coil delta T of just above 6 degrees F. So for transparency's sake, the building was designed originally in the 1940s with a dedicated 6-degree chiller in the basement of this building. And that chiller was removed when the building was put on the central cooling loop, which was fueled by a 12-degree F cooling plant. But obviously, or maybe not obviously, but factually, they did not pull all of the 6-degree coils out of all of the air handlers, and so they wound up having some difficulty matching a 12-degree chiller with some 6-degree coils. So basically, it had very large coils, taking a lot of water to create the cooling, and the energy valve was put into place to see if we could slow that water down and demand higher delta T and still satisfy the spaces. So we had a great success there. This project's a few years old now, but we were there in the summer of 2010 just kind of doing some research and measuring what was going on, and then in the same time period the following year with delta T management in place, we were essentially able to double the delta T performance in that building. So remember, we said before that flow and delta T are inversely proportional. So if I double my delta T, that means I cut my flow in half. So they're using half as much water in the same building, in the same equipment, at the same time of the year, essentially similar or the same type of loading. And in this case, Boston in the summertime, if you have not been there, is quite hot and it is quite humid. And so we are satisfying a great deal of sensible and latent load in a project such as this. So in 2003, Dr. Gregor Henze from the University of Colorado wrote a fairly detailed field study report of what went on at MIT. and you could see the cut sheet of the top here on the slide. If you look in the handouts panel of your webinar, the little thing that popped up when you came in the webinar, there's a few handouts, and one of them is called Energy Valve Field Study.pdf, and that is the full copy of this report. If you'd be interested in reading it, it's quite fascinating. Well, it's fascinating to me, but I'm an engineer by education. It's not fascinating to everybody, but it's an interesting scientific report if you wanted to read a little bit more about it. And while Mark Touillard is listed as an author there on the bottom right, he is a BLEMO employee. For the most part, he was there to make sure that all of the facts were correct about the BLEMO product and how it works, but mostly this is an independent document written by Dr. Henze. The second case study I want to talk to you about is the University of Miami, and this one came out quite a bit differently. BLEMO has a customer in the Miami area who is a performance contractor, and he took the energy valve to the University of Miami with the intent of saving them a bunch of energy under a performance contract. And so this data that we have here comes from the retrofit of the Rosenstiel building at University of Miami Hospital. There was 11 air handlers, about 2,600 tons of cooling. And when they got there, they were pumping over 10,000 gallons a minute through the building at about a 5.5 degree delta T. Each of the air handlers was retrofit, all 11 of them, and we were able to get delta T to be raised from 5.5 to 10.5 degrees Fahrenheit and cut the flows from around 10,000 to right about 5,600. So substantial reduction in the amount of water used to cool the same space, the same amount. And in his performance contract, he wrote the following figures. So these are not BLEMO numbers, but his. He estimated about $66,000 a year in energy savings from that building and about a 3-year payback, which included the cost of the energy valves and his services, you know, whatever he had done for them. So this wound up being a good investment for University of Miami. And then the last case study I would like to share with you, and again, if you were with us last time, this will be redundant for you, but it's pretty poignant, so I like to point this data set out here. So this came from a large tech company in North Carolina, and we have not written a paper about this. We haven't gotten permission from the company to use their name or likeness or anything, but they did share with us the data from their facility. And what you're looking at is a bunch of data from a single energy valve. And the data's collected a little bit unusually. What you're looking at is tons of cooling across the x-axis and chilled water delta T in degrees Fahrenheit going up the y-axis. And each one of the data sets represents a different way the energy valve was controlled. So this was from a single energy valve that was on a single air handler. Nothing physically was changed from any of this data. All that was changed was the control strategy that monitored the energy valve or controlled the energy valve. So this bottom set of data here was when the valve was in what we call position control, which means that the control signal just controlled how open or closed the valve was. So this would be like a standard control valve in place. And you could see that the load range was anywhere from 45 to about 75 tons, and the cooling was done between 5 and maybe 7.5 degrees of delta T. Now, for fairness sake, there's a whole bunch of gray points scattered all over the rest of this graph, but the clear trend was in this lower range. So sometimes they got better performance, but more frequently than not, they were getting this 4.5 to 7.5 degrees delta T. A couple of weeks went by and they changed their control strategy from position control to what we call flow control, where the control signal is now controlling how many GPMs of water go through that coil. So this would be in line with your pressure independent type control valve. And so now they have similar load range. It's a couple of weeks later, so the loading's not exactly the same, but we're still in that, you know, mid 40s to, in this case, high 60s tons range. And they're doing it on average at about 10 degrees delta T. So if they were averaging, you know, 6 before, now they're around 10, which is a sizable improvement. A couple of weeks go by and they engage Delta T Manager. Now, the Delta T Manager, you essentially there's a couple of ways to get your delta T management set point. In this case, they just sort of tinkered with it. You know, they probably set it at 12 and saw they could meet demand, and then they tried 13, 14, 15, 16, 17. At some point, they found they couldn't cool the space. So they settled right around 15 degrees F. And so now, with delta T management in place, again, that's still between sort of 50 and 70 tons range, they're cooling the same space with the same equipment with significantly less water because they have a higher delta T. So let's take a look at a single load point and try to quantify this a little clearer. If we look at 60 tons of cooling, in position control mode, 60 tons of cooling was done at 6 degrees of delta T, and if we use our tons, GPM times 24, all that stuff, we can calculate that 240 gallons a minute were required to create that 60 tons of cooling. In flow control mode, remember, it's the same valve on the same piece of air equipment. It's the same air handler, same valve, just a different control strategy at the valve. We didn't change the automation system at all either. Now we're at 10 degrees delta T. 60 tons of cooling gets us almost 100 gallons a minute less to create the same amount of cooling. And then when we put delta T management in place, we're now down under 100 gallons a minute. So 96 gallons a minute where we started at 240 gallons a minute to cool the same space, the same amount with the same equipment. So we used 40% of the original volume of water to cool the same space, the same amount. And so that's why we're really excited about this technology. Now, granted, in this case, we started with an air handler that was running a 6 degrees delta T, and it probably had a 16-degree coil in it. So we had a substantial problem which we could correct. But the impact shows that the physics behind this is valid. We can use less water in a lot of cases to meet the same demand. So the one last thing I want to remind you about before we close out and go to the question and answer session today is that the energy valve is not sort of magical. It doesn't make your coil behave better than its design. What it allows you to do is operate your coil at its design. What we see most places is that we have 16-degree coils in place that are operating at 8, 9, 10 degrees F, and then I have a 16-degree chiller plant that's running at 8, 9, 10 degrees F. All we're doing is taking the equipment and forcing it back to the conditions in which it was specified in the first place. So I want to thank you for joining me today. We're very happy to have you all on the line and join us today. If you have questions that we don't get to today or that you think of later on, please utilize marketing@us.belimo.com. The website, or excuse me, the email address is posted on this slide. So maybe just jot that down real quick. We'll answer 100% of the questions that come in if they come in through that way. And otherwise, I'm going to turn this back over to Lisa, and we'll go ahead and take your questions, should you have any, and we'll do our best to answer them. Oh, before I do that, I'm sorry, one last thing, Lisa, I cut you off there. There are 3 handouts attached to the presentation. So the white paper field study report on MIT is on there. The other thing that's on there is the full energy valve technical documentation, which includes the BACnet PIC statement and all of the wiring and installation instructions. And then there's just like a simple, straightforward product brochure. So if you want to know a little bit about energy valve or a whole lot about it, there's a few options right here in the handout section. Thanks, Lisa. Sorry for cutting you off there.
Not a problem. Thank you, David. We'll now take questions and answers. Please type your questions into the chat box. And I'll read them out loud and ask David the questions. David, we do have one here where it's saying, is the power output formula applicable to the system with glycol?
Yes, it is. There may be some slight variations if you have water additives, and I don't know off the top of my head what they are, but they're quite similar. And frankly, even if they're scaled, what would be scaled is that 500 number. There's still a relationship between flow, delta T, and B2H, and that you can't change that. So those 3 things have a relationship. If there's a skewing from the glycol, you know, the specific gravity of the fluid, that might change that 500 number, but it isn't going to change the fact that flow and delta T are inversely proportional at fixed load.
Okay, and also we had another question, is can we get a copy of the presentation? The presentation is recorded and it will be on belimo.us website, and all the attendees from the webinar will also get a link to where the recorded presentation is. One other question here is, in your example on the screen, how many hours of the year was the coil oversupplying? It was the gray part of the screen you showed where the BTU valve would save energy.
I don't know that I have year-over-year data on the specific examples that I use. So if I gave you a number, I would just be making it up, and I don't want to do that. The reality is that what we see, and I'll just use chill water as an example, is that we typically see large delta T problems in the shoulder seasons and into the high demand seasons, and then it seems to improve in high demand seasons, which actually makes sense. The higher your load is, the harder it is to overflow your coil because you have so much load. And so we would have to break it down differently to figure out the number of hours. I think on the MIT project, it may be listed in that field study report. We do have data specific to number of hours per year or percentage per year where the delta T manager was functioning and where it wasn't. That type of stuff typically is derived more from the facility managers at the facilities these valves go in. If they're really in touch and tracking their system, they have a pretty good idea of how frequently they're operating in low delta T zone.
Okay, and how about controlling the delta T at the chiller and control the flow through the chiller with pumps on the VFD and not on the air handling units? Will this do the job?
Depends on what job you're trying to do. So there is a couple of ways to approach this problem. You can create chilled water as efficiently as you possibly can. And that's what you're talking about here, is really forcing the water to slow down at the chiller. But if you don't have control of your coils, what will likely happen is that some of them will be starved. Because you're going to provide overall less flow. Like the building is demanding this high flow because we're having inefficient heat transfer in certain spaces. And those places will still demand high flow, and so that if your overall head to the building is reduced, then we have the potential to sort of starve far out. So there's plenty of people selling solutions in the market to optimize your chilling operation. And frankly, they're fabulous, and they do a good job of that. But if you can't control how your heat is transferred at your space, you're always going to have potential for either running out of water or creating inefficiencies. There's just going to be places that are using twice as much water as they need, and that's got to come from somewhere.
Okay. And can the BAS read the temperature, and can it override or change the delta T set point automatically?
So that's a great question, actually. The energy valve is a BACnet device. If you're connected to it via BACnet, the answer to all of your questions is yes. And so you can write a routine such that the automation system will disable delta T manager under certain circumstances that you would outline. So as I said, the PIC statement is in that tech document if you want to take a closer look. But basically, you can see the supply and return water temperatures, you can see the flow, you can see the BTU production, but you can also see and command the delta T set point and enabling or disabling delta T manager altogether. So just as an example, let's say you went into it's evening time and you're going to go into a heavy economizer mode and you're bringing in tons of cool air from the outside. Well, it's really hard to hit delta T set points if you're blowing cool air across your cool air, your chill water coils. And so in a lot of cases, people will write a routine that says disable delta T management when we go into economizing mode above X% open on your outside air damper or something along those lines. But yes, we can control all of those things.
Okay. And then somebody would like to know if they'd be able to get the slides to the presentation.
I don't have a problem producing there's a function in PowerPoint called a PowerPoint show, where I can give you the slides where they're essentially not editable to you, but you can reproduce them or show them off. And Lisa, I don't mind making that available to people. We've done that in the past.
Okay, great. So Peter, I will make sure that you get that. And if there's anybody else that would like that, just email us at marketing@us.believo.com. Another question here is, in a data center, we have lots of air handling units fed by using chilled water system. We have Villigent control systems which optimize space, temperature, and switch on and off air handling units. How we can implement it? Note that it's very important, I'm so sorry, this is a long one, to have specific cooling requirements at each rack.
Right. So in what we would consider a data center, similarly to how we would consider like an emergency room or an operating suite or something like that, maybe an operating theater more than an emergency room, as a critical temperature environment. And so when you do that, you're always weighing occupant comfort or space condition versus energy savings. And that's what's kind of neat about Energy Valve, is that you can choose higher or lower demands for delta T based on how critical that space requirement is. And as we responded to the previous question, or maybe it was 2 questions back, we can always write a routine that says, when we're not effectively cooling this space, immediately disable the delta T management. And so there's a few strategies you can put in place to address those, to make sure that even in critical zones, we're still be able to get the energy savings and the higher level control that we're looking for with something like the Energy Valve, without being nervous that we're going to create a problem in that space. And so that's an interesting one. If you're a data center person, it would be interesting to take a look at our upcoming webinar, and I think it's actually a couple of months out. We kind of take a break during the summer from webinars because people don't tend to show up as much, but we're going to have one on power control, which actually is a functionality in the Energy Valve that allows you to correlate your control signal to how many BTUs are produced at your coil. And so using that in conjunction with delta T management can almost essentially ensure you're always producing the cooling you need in that space. So a little teaser for next time.
Okay. So the valve runs independent of the building automation control?
Only when we violate the delta T threshold. So like all day, every day in a well-designed building, the delta T manager theoretically wouldn't come on. The only time it ignores the automation system is when we're in violation of that delta T threshold. So we set it at 12 and it's running at 12 or 11, 10, excuse me, it's running at 12 or 12 and a half or 14 or whatever. We're totally listening to everything that the automation system's asking for. It's when it gets, about a degree or so below that value. So we're at 12 degrees, now we're at 11 and a half, we're still listening, we get down to around 11, and I don't remember the exact number, but we could find out. At that point, the Energy Valve would suspend the direction of the automation system and start reducing the flow to push that delta T back up. But the rest of the day works just like any other high-quality pressure-independent valve.
Okay. Again, somebody had said, how can we download this webinar again today? It will be sent out to you after the recording later, early afternoon to everybody. Somebody said, good presentation. If you're controlling only delta T, why the energy meter? Can you define what the energy meter you mentioned?
Okay, so the energy meter is just sort of a function of what this product is. So the valve's electronically pressure independent, which means it uses a flow meter to become pressure independent. And then we're measuring delta T. So if I have flow and delta T, that is a BTU meter. And so it's there, we might as well use it. So the BTU meter function has nothing to do with the delta T function. They're both separate and distinct. They're both beneficial, but they don't really interact. So the metering portion, again, if you're looking at the image on the screen in front of you, the valve portion itself on the left side with the actuator is a characterized ball valve, and then on the right side with the kind of square looking head on it is an ultrasonic flow meter, and then obviously we have the two temperature ports. So now we're able to measure the amount of BTUs being produced at that coil. Whether that's a value to you or not is totally another question, but that just kind of comes with the product because that's how it's built.
Okay. And this question I'm not extremely familiar with. It says, I have a primary pump, maybe pump, it just says pump set with 150 TR chiller. I get more than 5 delta T. Any suggestions?
I'm assuming what he's saying is that he has a variable primary chiller set up and he has a low delta T. If that's the case, the energy valve delta T strategy works well on variable primary or primary secondary pumping strategies. And again, what we're trying to do is just force the building or buildings, depending on if you're a campus or what have you, to utilize less water. Once we do that, the pumping will go down, your chiller will be seeing less water and higher delta T. So as we slow that water down, the return water's warmer, and so it hits your chiller warmer, and so you're getting a higher delta T as you bring it down. So what you're looking at there is a fairly typical scenario where energy valve can come in and start to correct the vast majority of what's going on there. And again, it depends upon how your building or campus is set up, but we'd be happy to explore that with you if you'd like. So let us know.
Okay. Have you ever witnessed the delta T across the coil go over the design delta T during low load conditions? Like let's say 16 delta T from a coil designed at 12 delta T using the Belimo valve.
I'm not sure I 100% understand the question. I think what he's asking is, could we force a 12-degree coil to do 16 degrees of delta T? If that's what you're asking, yeah, it depends on how oversized the coil is, to be frank with you. So at the MIT case study, we forced a bunch of 6-degree coils to get 12 degrees of heat transfer. If he's just asking if a 12-degree coil can go to 16 degrees on its own, yeah, absolutely. It just depends on how the heat transfer in the space is working. We see issues with that because most places can't control their low flows as much as they would really like to. So they wind up with low delta T's at low flows based on the fact that they're just pumping too much water for the load in the space. So remember that when we talk about load, the load is defined by what's in the space, not how much hot or cold water you throw at it. And so if I have a really low load in the space and I'm dumping tons of water through there, my heat transfer is going to be lousy, and so I'm going to have low delta T. If we have that under nice tight control and we have low flows, we're going to have much higher delta T's to satisfy the low loads.
Okay. I think I'm going to take two of the questions and combine them. One of the questions was, so the valve consists of a flow meter, 2 temperature sensors, and a BTU meter. And then the next question after that is the valve a pressure-independent valve, or do you need additional pressure control strategies for good valve authority?
Okay, so I think I may have answered both of these questions with a few questions back, but to answer them directly, the energy valve is fully pressure independent on its own. So it doesn't need any pressure devices. It doesn't need a balancing valve. It works just like a pressure independent VAV does on the air side, in that we're just measuring the water flow and reacting to the water flow. And so if you have a 100 GPM coil and you're sending it a full control signal, 100% control signal, we're going to modulate the valve to maintain 100 GPM through that coil. And so that's how it's pressure independent. It's pressure independent electronically, which is different than if you're familiar with Belimo products like the PI-CCV is our mechanical pressure independent. And there's a whole bunch of other different types of things going on there. In this case, we're doing it electronically. And to answer the other half of that question, or the other question is, it has a flow meter and delta T sensors that is the BTU meter. So there's not an additional piece of equipment in there. A BTU meter is a collection of flow measurement and delta T measurement.
Okay, we'll take this last question. If you improve your delta T from 6 degree to 12 degree Fahrenheit, what return on investment could I expect if I was replacing a 12-inch chilled water valve, not including labor to install the valve? What is the general return on investment you see? Is it cost effective?
Well, I can't answer your question exactly, but I'll give it a swing. If you change your delta T from 6 to 12, you're cutting your flow in half. If you cut your flow in half and you apply pump affinity law, it means you're cutting your pumping costs to that particular place by 7/8. So there's, first of all, the pump affinity law is not perfect in terms of it's correct on paper. In real life, it might not be 87.5% reduction, but it might be 80 or 76 or some big number. So you're talking about a huge reduction in the amount of water and pump horsepower going into that. One of the things we did not talk about is the offering for Energy Valve. Energy Valve is only available in this case up to 6 inches, which is about 713 gallons a minute, I believe. So we don't have a 12-inch Energy Valve. But to answer the question you asked, the potential energy savings is enormous for that much flow to be cut in half. And again, I don't know, I can't throw a number out at you how that's going to pay itself back off because I just don't know enough about your system and where it's going. But I would certainly encourage you to look into it with that type of change in delta T on the horizon. Just like you saw on that last slide we showed, changing the flows that dramatically is possible.
Okay, great. Well, once again, thank you everyone for attending today's webinar. I'd also like to thank David Kandel. If you should have further questions, please email us at marketing@us.belimo.com. If you include the state that you're from, we can make sure that the regional application consultant can contact you directly for that location. Have a great day.